Hello students, welcome to the 8th lecture on this alcohol, phenol and ether chapter. Before going to discuss the relevant topic in this lecture, first let us understand what we have learned in the previous 7 lectures. In the first lecture, we have discussed about the introduction and classification of all these 3 compounds. In the first lecture, we have discussed about that. Actually, what is alcohol, what is phenol, and what is ether. Basic things that we have discussed in the same lecture. This is lecture number 1. We will also discuss about the classification. How do we classify all these 3 compounds? In the second lecture, we have discussed about the nomenclature, that is the common name and IUPAC name of the 3 compounds. In the next lecture, that is in the lecture number 3, we have discussed about the preparation of the alcohol. How we can able to prepare the alcohol in different sources and different methods that we have discussed. In the 4th lecture, we have discussed about the physical and chemical properties of the alcohols. In the 5th lecture, we have discussed about the identification of the alcohols. Suppose one sample of alcohol given to you and you have been said that to identify it. How do you be able to identify it? That we have discussed in detail. It is basically the 3 tests that we have discussed in this lecture, that is the Victor-Meyer test, Lucas test and hot copper test. By this way, by these techniques, we can able to understand about the nature of the alcohols, whether the alcohol is first primary alcohol, secondary alcohols or tertiary alcohols. And in that lecture, we have also discussed about the preparation of the phenols. In the 6th lecture, we have discussed about, again, a very important thing, that is the physical and chemical properties of the alcohols. And in that lecture, we have discussed about those chemical properties which concern with the OH group present in the benzene ring. In the lecture number 7, in the last lecture, we have discussed about the chemical reaction that is being undergone by the benzene ring in the alcohol. That is the electrophilic substitution reactions undergo by the benzene ring. These are all the 7 lectures that we have discussed. And if you have not watched this lecture, you should watch the lecture and you will be certainly benefited out of this. In the 8th lecture, that is in this lecture, we are going to discuss again a very important thing, that is the preparation of the ethers. So heading of today's lecture is preparation of ether. This is K.K. Mukherjee in the Science with Mukherjee Sir YouTube channel. Preparation of ether, when we are talking about the lecture number 2, we have discussed about the different types of ethers. That is one that is symmetric ether and other is unsymmetric ether. Symmetric ether is those ether where both the alkyl group is same. That is diethyl ether. You can see here both the alkyl group are same. Unsymmetric ether where the alkyl group is not same in the ether. That is ethyl methyl ether. This is also unsymmetric ether. So in this lecture we will be going to discuss those preparation methods. Some preparation methods that we will observe that where it is basically solely that from this method you can able to the symmetric ethers, and another methods that will only for the unsymmetric ether. And there one very important reaction method that we are going to discuss, Williamsons synthesis, that is the both the alkyl, that is the symmetric ether as well as so unsymmetric ether you can able to produce. So first we will discuss that is the how we able to produce the symmetric ether from a different methods. First method that we are acid dehydration of alcohol. Alcohol, we can see it is a basic source of producing ethers by different ways. Acid dehydration alcohols, in this case what we find in presence of protic acid like H2SO4 or H3PO4 at a particular temperature, the alcohol is dehydrated to produce the ether. Here temperature is very important, because if we exceed that temperature, in other temperature ether will not going to be produced, the alkene will be produced. So reaction for this preparation of the ether is this. Here you can observe the two molecules of the alcohol has been simultaneously react with each other, and in presence of concentrated H2SO4 and temperature is 413 Kelvin. Here you can see there is a elimination of one molecule of H2O, that is why it is called dehydration reaction. So here in this process we can see this ether is being formed. This is, you can see, this is the symmetric ether. In this method we can only produce the symmetric ether. Number one, limitation of this process, and number two limitation, that in that reaction only the primary unbranched alcohol should be used. That can be easily understood from its mechanism. It is being prepared by three mechanisms, three steps you can say. Mechanism is one, that is the three steps. In the step number one, you can see there is a protonation of the alcohol. Alcohol is protonated, means addition of H plus ion, so it will produce this. This is called the oxonium ion. And here you can see this H plus has been added to this oxygen atom, where there is a lone pair of electron, and this lone pair electron will be taken by this H plus ion. When it is taken up, then it will be positively charged. In the second step 2 process, what we observe, there is a nucleophilic attack. In the alcohol, we understand that is a versatile compound, organic compound. It can be act as a liquefied as well as the electrophile. Here the another alcohol molecule which is not protonated, that will act as a nucleophile, and this will react there. The reaction is this. Here this attack is basically SN2 attack. SN2 we know that substitute nucleophilic bimolecular. Here this oxygen atom will be attached to this, and because this is a positively charged, it will take up this electron pair into itself, and this bond will be break, and there will be the production of this and H2O will be liberated. So dehydration reaction, you can say H2 has been liberated and there is an attack of nucleophile, the alcohol molecule to this carbon atom, and this H2 has been released and it will be produced. Now that is the third step, and the last step that you can see, step 3, this is the deprotonation. In this step you can see in this step what is going to happen, as it is a positively charged, the electron forms this OH bond has been taken off by this positively charged oxygen molecule atom, and it will be the ether. The ether has been produced with the release of H plus ion. So CH3, CH2O and CH2, CH3 and H plus ion. This has been produced. So ether has been produced. Now you can easily understand, this is the SN2 reaction is going on here. If it is 2 degree alcohol or 3 degree alcohol, at that time this addition of this alcohol to this carbon atom is not very easy, is not possible, because of the presence of the bulky group here. CH3 group is a bulky group. Here you can see there is only one group. When it is a 2 degree or 3 degree, then there will be the more number of the CH3 group. So at that time, this molecule, this alcohol molecule will not able to approach to this carbon atom, and this reaction, SN2 reaction, nucleophilic attack to this electrophile will not going to happen. So the ether will not going to produce from this 2 degree or 3 degree alcohol. Only the primary alcohol can able to produce this ether because of the steric hindrance of the H3 methyl group, that is you can see. So this is the main limitation of this preparation process, that it only been found out, it only been possible for those primary alcohol, primary unbranched alcohol, and it is only in this process you can only able to produce the symmetric alcohol. Okay, so this is the acid dehydration. Second reaction, second way, in this way also you can say, you can write this is for symmetric ether. Symmetric ether. Second process, that is catalytic dehydration. In this catalytic dehydration, you can see that it is dehydrated in the presence of a catalyst. This catalyst has been heated at the temperature, very high temperature. The reaction of this dehydrated, and it is going to produce the ether. Two molecules of alcohol in this way, that how we have discussed here. In this way, this alcohol has been produced, and it will be H2 has been removed from the alcohols, 2 molecules of alcohol, and it will going to produce this ether. So this is second way of producing the ether. Now we are going to discuss how we can able to produce the unsymmetric ether. Third reaction, in this way you can able to produce the unsymmetric ether. It is the addition of diazomethane. CH2N2, because this is the methane, and here you can see there is a diazo group, that is N111 N, this is the diazo group, and when we add this in the alcohol or a phenol, it is going to produce the ethers, and the reaction is this. It is going to produce this ether. It is the unsymmetric ether. You can see there one alkali group is methyl and another is ethyl. So you can be able to produce this methoxyethane. This alkali is methoxyethane, or you can call ethyl methyl ether. But here you have to use one catalyst, tetrafluoroboric acid. You have to use this catalyst. But when we produce the phenolic ether, at that time we do not have to have requirement of this catalyst. This catalyst is not required, but without this catalyst you can able to produce this ether, and this ether is, it is called anisole. Anisole. So by addition of the diazomethane, we can able to produce this unsymmetric ether, both the phenolic ether and the normal, that is the alkyl groups has been attached there in this ether, that you can see. The fourth, that is we are going to discuss, the addition of alkene. Addition of alkene to alcohol. In this way also you are going to produce the unsymmetric ether, as for example, propene. When it will act with this ethyl alcohol, suppose this is the ethyl alcohol, at that time there will be the, in presence of concentrated H2SO4, it will going to produce the unsymmetric ether. There will be the addition of this ethoxy ion to this carbon atom and this H plus ion to this carbon atom, and that will going to produce these ethers. So you can see CH3, here will be addition of this so this ether is produced, that is the name of the ether, that we can see here, butyl tertiary butyl ethyl ether. This is the tertiary butyl group and it is the ethyl group. So it will produce the tertiary butyl ether. By addition of the alkene to the alcohol, in this case, these alkoxy ions has been attached to this carbon atom as per Markovnikov rules. Markovnikov rules. Fifth, that is the next way that we can able to, that is very important, that is the Williamson synthesis. Williamson synthesis. thesis. In this way, that is a very important process. By this way, we can able to produce the ethers, both the ethers, that is the symmetric ethers and unsymmetric ethers, we can able to produce by reacting with the sodium or potassium alkoxide with the ethyl halides. The reaction is this. Sodium ethoxide that you have used, sodium ethoxide and it is methyl iodide. When this has been heated, these two components, the component has been heated, it is going to produce the ether. Here we can see that the ether has been produced, which is unsymmetric ether. But if we use here the ethyl iodide, then it will again produce the diethyl ether. In this way, you can able to produce both the symmetric ether and unsymmetric ether in this compound. Now, in this way, you can also produce the phenolic ether you can also able to produce. As for example, C6H5OH, C6H5ONA, that is sodium phenoxide plus if we take this CH3Br, suppose methyl bromide, and when it is heated you can able to produce this ether, that is 66H5OCH3 and this is NaBr. So here you can able to produce that by taking the sodium phenoxide and CH3Br. But here one thing that we have to remember, that if you take the bromobenzene, suppose this is bromobenzene and sodium ethoxide, then this will not be going to be produced because the bromobenzene is not so reactive towards this reaction. This reaction is basically the nucleophilic substitution reaction. So this reaction is not very much feasible. This reaction is not happened because the bromobenzene is not reactive against the towards this nucleophilic substitution, but the alkyl halides is much more reactive than this. So this reaction is not feasible. This is not going to happen. Now we are going to discuss the mechanism of this reaction. The reaction is basically happened in the SN2 mechanism. SN2 mechanism that we have already discussed in the haloalkanes, haloiodine chapter. The mechanism is like this. Suppose when here this alkoxide, that is here the ethoxide ion will be attached to this this we have taken this will be basically a SN2 mechanism, and this ethoxide ion will go to this, will attack this carbon atom, and this bromine being a very good living group, it will depart it from here, and you will see this will attach there, and this is going to produce this ether. But if we choose this tertiary alkoxide, that is butoxide, sodium butoxide, as for example this, at that time this will be attached to this, and it is again follow the SN2 mechanism, and it will going to produce this ether. This ether will be produced. This ether is tertiary butyl ethyl ether. Now, if we choose this way, instead of this tertiary sodium alkoxides, this is sodium tertiary butoxide. This is sodium tertiary butoxide. Instead of this, if we use the tertiary butyl iodide. This is tertiary butyl iodide, and this is sodium ethoxide. Instead, this we have choose before. Now we have choose this reagent. At that time, this reaction will not be the SN1 reaction. This will two reaction. This will be SN1 reaction. At that time, this will not, this alkoxide, this ethoxide ion will not going to approach this carbon atom, because it is already crowded, and so it is not going to be, the reaction will not going to be happen. So at that time, what is going to happen, there will be the elimination reaction. This hydrogen will be taken up by this ethoxide ion, and there will be the elimination of this, and there is a formation of the alkene. So you can see Here double bond has been created because this hydrogen atom has been taken up these ethoxy ions, and this will going to produce this alcohol, and with this alkene is produced, and this will going to happen this. So here you can see that is 2-methyl propene is being produced instead of the ether because of the choice of this tertiary butyl iodide. So in this Williamsons synthesis, we have to always be cautious, be careful that we choose the alkyl halides that will be the primary, not secondary or tertiary, but we can choose the ethoxides, that is the alkoxides, any kind, that is 1 degree, 2 degree, 3 degree, it is possible, and in this way we can able to produce this unsymmetric ether or symmetric ether. So we have discussed that is different methods of these ethers. That is, first we have discussed the acid dehydration, then we have discussed the catalytic dehydration, then the addition of the azomethane, then Williamson synthesis, additions of the alkenes, and that is all for today's lecture. We will meet in the next lecture with the properties of the ether. Thank you very much for watching.